Hello everybody. Well, in this video we're going to look at the idea of a Taylor polynomial or a Maclaurin polynomial. A Maclaurin polynomial is simply a more specific type of Taylor polynomial. Taylor is the more general type of polynomial. Maclaurin is very specific. More on that later though. So what is a Taylor polynomial? A Taylor polynomial, quite literally, is a polynomial that approximates a more complicated function. So in the gray, I have the sine of x. And this line right here is going to be my approximating polynomial. And I'm going to set some conditions for this approximating polynomial. First of all, it has to have a center. So where do I want my polynomial to be centered at? Do I want the center over here at a negative value? Do I want it at 0? Do I want it at some positive value? And for the purpose of this video, we're just going to look right here at pi over 2. Okay, so the conditions I'm going to set on building my polynomial are the following. I want my original function, sine of x, and my polynomial to have the exact same function values at my center. So my center is pi over 2. The sine of pi over 2 is 1, and it looks like my horizontal line or approximating polynomial, its value is also 1. Now the next condition we're going to set is we want the first derivatives to be the same. Okay, so you can see that the derivative of sine at pi over 2 is really the slope of this tangent line, and the slope of the tangent line is really the slope, well, sounds redundant, it's also the derivative of the blue line. Okay, so both the sine curve and this blue line have a slope of 0, at least right here. And you can see that if I zoom in on this a little bit, if I zoom in and sort of move my center around a little bit, whoops, that's not what I wanted, sorry. And I move my center, if I move my center to 0, now remember that I only have a first degree polynomial. So if I zoom in, that blue line and the sine curve look virtually the same, at least if we're in between negative 0.5 radians and maybe 0.5 radians. Okay, but further out, this line does a horrible job of approximating my sine curve. So let's move the center. Let's move the center back to pi over 2-ish. Can't get it exactly there, but that's pretty close right there. Well, what if I wanted to not only have the first derivatives be the same, but I want the second derivatives to be the same. In other words, I want them to have the same concavity. Right now the line has no concavity. So if I say let their second derivatives be the same, then you could see that now I have this parabola. This is a second degree polynomial. It looks like I got really better at approximating the sine curve in between these two values here. Again, I can move my center around. And you can see that my second degree polynomial is really good at approximating that sine curve as long as we're evaluating angles centered right around my center, or close to my center, I should say. Well, we could get even better than that. We could say, what if we want the function value to be the same at the center? We want the first derivative to be the same at the center. We want the concavity or the second derivative to be the same at the center. Well, now we want the third derivatives to be the same at the center. So if I let the third derivatives be the same, you could see that my graph shifted, and I now have a third degree polynomial. Okay, it's kind of hard to see, but there's the third degree polynomial right there. Okay, I can continue this. What if I want the fourth degree to be the same? The fourth derivatives to be the same, the fifth derivatives to be the same, sixth, seventh, eighth, ninth, and finally 10th. Okay, so if you look at both of these curves, you look at the original sine curve and you look at my 10th degree polynomial, what's going on here? I have a center. The center is right where my mouse is. And what's going on at that center point? Well, the function values are the same, and the first through the 10th derivatives are identical. And what that's doing is it's building a polynomial that looks to be laying down pretty precisely on the sine curve itself. Okay, to drive this point home even further, I could look at a numerical representation. Okay, so here in the red is my sine curve, and in the blue is my third degree approximating polynomial. And you could just compare the table values. The sine of 0 is 0, and my polynomial, and you don't know where that polynomial came from, and that's okay. I'm going to show you how to get that in the next video. But if I plug 0 into this polynomial, I also get 0. So condition number 1 is met. The function values are the same. Now, the first through the third derivatives are also the same. So let's see how that affected the accuracy. The sine of 0.1 is actually 0.0998. And you can see that my polynomial with just a third degree polynomial is 0.0998. Sine of a half a radian is here, 0.479, and my approximating polynomial is 0.479. Now you can see as soon as we move out to 1, you could see that my polynomial starts to have a little bit of error in it. And then you can see that at 2 radians, my approximating polynomial is not very good at all. So where do these points live? There's the actual function values that I'm interested in, and there's my approximating function values. Okay, well I can actually get even more accurate. Okay, so pay attention to this value right here. This is not a good approximation. Okay, this is 0.666 and this is 0.909. How can I get even more accurate? Well, if I add a term to it, and again, you don't know where this term is coming from. In the next video, I will show you. Whoops. Okay, what's going on here? Divided by, there we go, 120. Okay, you could just see from the curve that we got more accurate. And now what I'm going to do is I'm going to cut and paste this term right here. Now remember, pay attention to this value right here. Watch what happens. Okay, and you can see that we just got way more accurate. You can see that the dots match up just a little bit better. Okay, so I gave you a graphical idea of what a Taylor polynomial is and a numerical approach. Let's just go look at one more type of function, and in this sketch is e to the x. The red is e to the x. We're centered around 0, and you could see already this black line, which is going to be my approximating polynomial, they have the same function value at 0. It looks like they have the same slope at 0. Now let's give them the same concavity at 0. Now they have the same concavity. Now let's let them have the same third derivatives, the same fourth derivatives, 5th, 6th, 7th, 8th, 9th, and 10th. Okay, so you could see that my 10th degree polynomial is virtually indistinguishable from e to the x, at least from around right here all the way out here. In fact, you can the black line appear, the black curve appears to lay perfectly over that. I have to really zoom out. I have to really zoom out in order for you to see that it sort of gets away from it a little bit. And there we go. Okay, so you could see that it's not laying on it perfectly forever. But this is only a 10th degree polynomial, and you could see that right here we're way up at like 600 right here. And what does that mean? That means that I'm out here at 7-ish. So e to the 7th power is approximately like plugging 7 into my 10th degree polynomial. Okay, just a little bit of fun here. I like watching the animation. And then let's go back to a 10th degree. And again, this is the computer building the polynomials. These are the different terms. Turns out these are really easy to do. Again, coming in the next video. Let's go back to the sine approximation, and let's just watch this animation. Okay, so there's a first degree polynomial, and then I'm going to jump right to the 10th degree. Okay, so there you go. In the next video, we're going to compute these by hand. But in summary, in conclusion, a Taylor polynomial is a means for us to approximate a more complicated function. And in fact, your calculators and computers, when you are evaluating complex functions, it's probably using some sort of approximating method. So I hope that helped. I will see you in the next video.